In this video, I'll provide global perspectives on groundwater resources and focus on one regional example, the Ogallala aquifer of the U.S. I'll highlight the collision between science-based recommendations and political realities. Groundwater is a natural resource that can be exploited. Withdrawal of groundwater faster than it can be recharged is groundwater mining, and that's not sustainable. When groundwater is gone, in many areas of the world there are few alternatives. M. King Hubbert, a very influential scientist of the 20th century, made seminal contributions in geohydrology in the 1940s and in petroleum geology and geophysics throughout his career. In 1956, he created much controversy when he predicted that despite increasing production of oil in the U.S., that oil production would peak around 1970 and decline thereafter. When that prediction turned out to be spot on, he became quite famous. He wrote in 1975, "Aspects of our current economic and social thinking, which are based on the premise that rates of growth can be sustained indefinitely, must be revised." Failure to respond promptly and rationally to these impeding changes could lead to global ecological crises in which human beings will be the main victim. Here is a map prepared by the United States Geologic Survey that indicates the reliance of population in the U.S. on groundwater. The numbers on each state represent the percentage of the population using groundwater for domestic water source. You can see that in nearly every state there's a significant fraction of the population. Even in a surface water rich state like Washington State, 61% of the population uses wells. In states like Florida, it's 93%. Nowhere is the fraction particularly low. On a global scale, it's useful to plot population density in blue, cool colors and water scarcity in warm colors. Where population is high and water is low, there is a clear crisis in the making. In the United States, we have the Southwest. Now, the population there is nothing like China or India, 16 million people, but we do have a ongoing crisis of not enough water for the people. In Pakistan, there's 133 million people living in water-scarce regions. In China, it's almost 500 million in water-scarce regions. 250 million people in India are in water-scarce regions, and they have virtually no restrictions on pumping of groundwater, and depletion is accelerating with prolific use of electric pumps. Israel is also a location of high demand and low availability. So let's focus just on the United States for a moment. The Ogallala aquifer is described as the leading irrigation area of the Western Hemisphere. It covers nearly 500,000 square kilometers, encompassing 8 states. It is Pliocene sands, gravels, silts, some 30 to 300 meters of saturated thickness. The total storage of water in the Ogallala aquifer is equivalent to a small Great Lake. And here's a map showing the great regional extent of the Ogallala aquifer, as well as regions in which the water level has dramatically decreased in recent decades. And it's all decreased because farmers are setting up pumps, as shown in the photograph, in order to irrigate their farms and pastures. The geology of the Ogallala aquifer is relatively simple. From the Rocky Mountains going eastward across the Great Plains, the land slopes downwards. There is deeper level layers of impermeable rock overlain by the sands and gravels. The water comes through the sands and gravels and then flows down the interface between the confining layer and the surface. Since the 1940s, the level of water in this aquifer has in some places decreased by as much as 30 meters. Currently, the average rate of mining of water, i.e. taking out more water than is recharging, is just short of a meter per year. These sands and gravels are fairly permeable, so contamination from agricultural sources is increasingly reaching the aquifer and contaminating the water. So chemical agriculture began about 50 years ago, and that material is finding its way now into the aquifer. So all of this is well known by the people in the area, and stakeholders in resources of the Ogallala aquifer have come together and put together a document called Proposed Desired Future Conditions for the Ogallala Aquifer. This document is in the online resources for the course. Reading this document, you can find the collision between what's a rational sustainability goal, i.e. science-based, understanding the rate of recharge of the aquifer, and what policy tools or laws are available to enforce sustainability goals, and finally, what political realities exist in which this is all taking place. Clearly, if the stakeholders do not accept the sustainability goals, somebody's going to be voted out of office and laws are going to be changed. So, the stakeholders came together, they formed a management goal for the next 50 years of the Ogallala aquifer, and this management goal does not sustain the level of water in the aquifer, it merely slows down the rate at which it's depleted. So the prediction is by 2060, the remaining amount of water in the aquifer on average will be about 60% of what it is in 2010. And you notice from the chart shown here that in some areas the depletion is severe and only 38% of the resource will be remaining in 50 years. So even with goals to reduce the usage, there's as much as 70% of the water is going to be gone in 50 years. The remaining water everywhere will be harder to pump because it's deeper, and it's going to be more contaminated as the agricultural chemicals seep down into the aquifer. So within a generation, agriculture in the heartland of the U.S. is going to experience a significant challenge, and we do not know how this challenge is going to be confronted. So that's the end of sustainability talk. Coming up next, I want to go into the details of the hydrologic cycle.